Hello, let's talk about the early history and the early of chemistry and some of these early chemical laws. Um, so, why do we need to even know about this early chemical history if it's not even what we're currently doing? So, a lot of times we have these preliminary models that were very primitive, that we're changing and we don't use nowadays. But I think it's really important that we can demonstrate what we mean by the scientific method. Watching how these models and these ideas about chemicals and atoms evolved really helps us see what we really mean by the scientific method and the nature of science and how scientists do science. So also, the model of the atom is actually kind of complex. There's a lot of little moving pieces to it. So we kind of start with this primitive one, and by evolving the model, it's sort of like we understand the primitive model, and then we add on some extra features, then we add on some extra features. So it's mentally a little bit easier to absorb in pieces. Also, there's going to be some chemical laws that we're going to be using as sort of ground rules, and we'll refer to them and assume that we all understand that these laws of multiple proportions and the Dalton's atomic theory, that we understand that that's something that we're building on. So just to kind of, we are standing on the shoulders of these early scientists. So I do want to sort of at least mention their names. They were pretty important. Sometimes the people who begin a field get very little credit because, as we say, we've evolved from there. But none of this later revolutionary work could have happened without somebody originally coming up with the idea of an atom. When Democritus came up with this idea that stuff is made of tiny materials, that's honestly a pretty big shift from where the world was at that point. And that was a very revolutionary thought. Now we assume, oh yeah, of course everything's made of atoms because that's what we grew up learning. So we had Democritus came up with this idea. Also, Empedocles was related. And then we have Aristotle and Epicurus also had a lot of philosophical ideas about what matter was. And then there was a lot of scientists, like alchemists really, who came up with, just did a ton of experimentation and came up with a variety of laws of like, hey, this is something that happens consistently. Hey, if you do this with this, this is what's going to be made. Particular of as Hayyan, I can't say it right, Jabir, but was a very influential Persian and usually doesn't get mentioned in the analogs of chemistry, but had this huge collection of all these reactions that then became something that people could build theories on. They had to have all these different ideas out there of like, hey, I have this huge compendium of all these things that can happen when you mix different chemicals. Paracelsus was another one. And then we come to this sort of modern age of science, as science is really becoming less about philosophy and religion and more a thing unto itself about understanding our natural world. And we had Boyle and Priestley and Scheele and Cavendish and Lavoisier and Proust, and a couple of these we're going to talk about in a minute. But they sort of now started saying, okay, we got to find some patterns here. Let's look at this. This isn't just random stuff. We have patterns here. And these are exactly the same kinds of things I'm asking you to do, is sort of notice things, observe things, kind of say, okay, I've done all these problems. Can I find the patterns? So I think these are good examples to go off of. So let's talk about a couple of these laws. There's 3 laws we're going to deal with: the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And they can be used to do some tricky problems that you think are impossible at this point, but you can actually do some interesting things with some mass analysis. So Lavoisier came up with this conservation of mass. The idea is that if you carefully weigh all of your reactants and you carefully weigh all of your products, it will always be the same. In other words, you can't have any mass disappear along the way, and you can't just like magically appear out of nothing. This is pretty important tied to this idea of atoms. If atoms can't be created or destroyed, then whatever you start with, you're going to end up with, and since they all weigh the same, we shouldn't have any change in mass. And we can use this in different problems by, if I know the mass of all of the reactants and products except for one, I can figure out that one. So I can give you, in a reaction with 2 reactants and 2 products, I can give you 3 of the masses and ask you to find the 4th. Of course, every reaction is different. What if I have one reactant breaking up into 2 products? Well, then I only need 2 of the masses to figure out what the 3rd is. And it can be either a reactant or a product. I do find one of the keys here, though, is that you really should write out the chemical reaction. Even if you don't know the chemical formulas, write it in words so that you say this and this, arrow, this. Then you can write the numbers underneath it, and it does help you make sense of the mass so that you're not subtracting when you should be adding and things like that. So if we look at this calcium carbonate, that's the name of that, decomposes into carbon dioxide and calcium oxide. Again, you don't need to know the names quite yet, but it's coming. So calcium carbonate decomposes into carbon dioxide and calcium oxide upon heating. If 10 grams of calcium carbonate form 5.6 grams of calcium oxide, how many grams of CO2 were released into the air? Notice that first sentence I need to kind of put into a equation. CaCO3 decomposes into CO2 and CaO. So that decomposes into is saying that's the change. So I begin with CaCO3 and it turns into CaO and CO2. So I'll just put plus signs in between them. Now when I go to put these numbers in, it's not so hard. So if I start with 10 grams of CaCO3 and I form 5.6 grams of CaO, whatever is left over on the right hand side has to be the carbon dioxide. So I subtract off the 5.6, I get 4.4. Where people go wrong is they try and do it in their head or in their calculator without writing it out. Write it out. Even if you use words, even if you didn't have the chemical formulas, you use like words, you say oxygen plus iron makes, and you put an arrow for the makes, rust. The next one is the law of definite proportions. A given compound always contains the same proportion of elements by mass. So in other words, regardless of whether I have a tiny bit of calcium oxide or a huge bit of calcium oxide, if I can determine the mass of the elements, the ratio of the calcium to oxygen in the small sample is going to be identical to the ratio in the big sample. Again, this is because we said that compounds are made up of certain ratios of atoms. So if it's 2 to 1 in terms of atoms, it's the mass of them are going to not change, and so I'm always going to have that same ratio. But again, it's always a ratio that we're comparing. So I need to have what is the ratio. So water is composed of hydrogen and oxygen. 18 grams of water is decomposed into 2 grams of hydrogen and 16 grams of oxygen. That tells me the ratio of the compounds, of the ratio of the elements in the compound water. Now I can ask you about a different sample of water. What would a 45 gram sample of water decompose into? So first I'm going to find the ratio. In this case, 2 hydrogen. So I can either do it as 2 grams of hydrogen to the whole thing, 18 grams of water, or I can do 16 grams of oxygen to 2 grams of hydrogen. So notice I've got two different, this is a ratio of oxygen to hydrogen. This is a ratio of hydrogen to water. This is a ratio of oxygen to water. Either way, I'm relating the two ratios, and I'm using that to compare to my new sample of 45 grams to break it down. The last one is kind of tricky because it's the ratio, and we were pointing out that these ratios are not going to change, and so I can use them. So the law of multiple proportions. So this was what Dalton said. Remember, no, we haven't gotten there yet. But Dalton says that we can make different kinds of compounds from the same two elements if we put them in different ratios. And basically, if I have two elements, form a series of compounds. So I might have two different compounds involving, let's say, calcium and oxygen. And so they're in different ratios. In the two different compounds. What makes the compounds different is that the calcium to oxygen in compound 1 is different from the calcium oxygen ratio in compound 2. However, if I take the ratio of those ratios, it will always be a whole number. That's what he's saying. So the ratios of the masses of the second element to 1 gram of the first element, so that's really a ratio, in one compound, ratio to that ratio in another compound will always be a small whole number. And that's, again, because it's really down to these atoms. So, like, this is an example. So, 2 compounds form nitrogen and oxygen. Compound A is 63% nitrogen. Compound B is 46% nitrogen. So I need a nitrogen to oxygen ratio for each of these two compounds, compound A and compound B. So how do I get it? Well, it tells me that compound A is 63%, I'm not saying the whole thing, but 63% nitrogen. So I'll put that on the top, and I want to know, well, how much is the oxygen? Well, if I had 100 grams, it would be 63 grams of nitrogen, and everything else left over would have to be oxygen. So I can do some tricky things here, and since this is in percent, and I know percent is out of 100, if I subtract that off of 100, I can find out the remainder that's the oxygen. Same thing with the compound B. So 46% is the nitrogen, 100 minus 46.67 is 53.33. That gets me the oxygen mass. So this would be one ratio is 1.75. This is the other ratio for compound B is 0.875. And if I take a ratio of those ratios, I get essentially 2. It's very close. It's, once we do rounding errors, it's 2, which means that compound A has twice as much nitrogen in it per oxygen as compound B. If I were going to take this and now try to come up with chemical formulas, I would say that the nitrogen is going to have double the subscript in compound A as it does in B. Makes sense, right? So those are some of these 3 laws that we can talk about, and we will practice some of those problems in class.